This first video shows the entire process with Joe installing the water bottle. He straps bungee around it to secure the water bottle in place. The bottle is lifted, and at the top right here, this black device is a kill switch to ensure that if the operator is careless and raises the bottle too high, that it will automatically stop to prevent any damage to the machine. The holder is rotated out of place and lowered back down again. In that was an empty bottle. Unfortunately, throughout the course of the semester, our full bottle disappeared on us. This video shows the time required to lift the bottle up. Apologize for the lag there. But the entire time to raise it from the ground is about 10 or 11 seconds, which met our calculations and what we were hoping for with our estimated time. This final video shows Joe out of the way, and so you can see the bottle as it's positioned into place above the dispenser and is lowered down. The strap is removed. And again, rotated out into place. While there are several steps in this process, we feel that they are fairly simplistic and allow for a successful product. With
Actually, this design was specifically pinpointed to the caps that actually have a male punch, a female cap and a male punch on the water cooler dispenser. We didn't want to go with the one that you actually have to remove because there's no way of actually removing the entire cap without keeping the water from flowing all over the place. So it's marketed specifically for that type of water bottle.
And in fact, essentially all water coolers that are now sold new work that way. It's more of an older design that has the removable cap.
Or it's a bayonet fitting? It's a bayonet fitting?
It's kind of, it has a male punch in the bottle that punches out a thing in the cap, or in the cooler there's a male punch that will punch out an area in the cap and open it under the weight of the water, I guess.
For our midterm presentation, we had a detailed picture of exactly that male punch and female cap. Unfortunately, we don't have it with us now. The tilt angle, we did consider that, but we felt that it was, at that point, it was going to be, are you talking about, well, what we were talking about is the tilt angle from letting the gravity pick up the bottle. And
I'm sorry, let me be more specific. When the bottle is at its peak, its highest distance, I didn't see any data regarding will that stand stay fixed? There's torque.
Tilting of the entire mechanism.
Correct.
Okay, we did consider that.
So actually, whenever we did the FEA, we put the whole assembly into the FEA. We only constrained the very bottom plates. So that way, when you put all the force on the arm, that it was actually deflecting a little bit. It was really kind of hard to see in the pictures, but it was deflecting about a couple of inches just by picking up the bottle alone. So that's how we kind of...
And what we took care of it is we actually installed the railing system onto a base plate. It's approximately 1.5 by 2.5 feet that stands next to it. So that actually is our footprint. It's a piece of wood that we installed this on to keep it from tilting over. So we have a larger stance to keep our center, our moment of inertia within that plate.
Thank you. That's a great presentation. I'm impressed.
Any other questions from the audience? Greg?
We kind of compensated for that by kind of trying to use longer roller bearings. Like if you can imagine, you distribute the frictional force over a longer surface area. But no, it didn't. I guess we forgot to.
The linear bearings that we have are actually 2.5 inches, 2.5 inches linear bearings. Yes, carriages.
Does it lock with the full bottle?
It does not lock with the full bottle. Actually, what we did find out is when the arm is empty, it becomes a little jerky. It seems just because the weight of the carrot itself causes that. I mean, it worked better with the loaded weight than what it did with the
So
other.
stride draws was taking the full moment of the, that's what you're using in your analysis.
John?
We do have one backup slide on FMEA as far as feather mode and effects analysis on it. We didn't know if people were going to ask that, but we did throw this in fact where the feather mode would happen and the likelihood of the event. Yes, and we did see that. And you know, fortunately, this is our prototype, and we did think that the way it is right now is in the resting position, that arm, since it's a 3-point pivot arm, will fold back on itself and onto within the railing system itself, not sticking out permanently. We do have, in our report, we do have future assessments of what we want to do, and that's one key point that we do need to fix.
Any other questions? Dave?
We have looked into that. Our biggest cost, quite honestly, is our winch. We spent $400 on that. If we were going to go with a regular motor on that, it would dramatically cut our cost down to about a third or a fourth of that price. We didn't go with that route because we needed a specific type of motor that will be able to avoid that the clutch will be engaged when the power is shut off, and that was outside our lead time to get our coaxing built. So we went with the next best thing is a winch, power in, power out winch.
Another thing to consider is that our prototype is made mostly of aluminum. We're better working with aluminum, but realistically, you'd probably make it out of a cheaper metal. Like, I don't know, I think steel's a lot cheaper right now. So, you know, if it was manufacturing, it would be probably a different metal. But with our experience in machining, we decided to go with aluminum where we could.
It could approximately accommodate 95% of the water bottles currently out there. The other 5% is they're either wider stance, our arm does not reach, or they're coming back that they accommodate a square bottle instead of a round bottle. And our folder is specifically for the round bottle.
All right. We'll have to move on to the next team, so thank you.